Hello and welcome to our lecture on the precession of a gyroscope. It's a very short lecture, a mini lecture of sorts, and I just want to talk about one interesting idea. Okay, so here we have the idea of gyroscopic precession. Maybe it's something you haven't heard of, maybe you've seen a gyroscope before. That's usually the most vivid demonstration of what gyroscopic precession is. Also, a top does it. Any spinning top, any toy that spins will precess as well. So what is it? Okay. So first of all, let's define what precession is. So the idea is that because torque, by definition, and this is the torque vector, mind you, is equal to the instantaneous change in the angular momentum vector. This is Newton's second law. Okay. So Newton's second law. Because of that law, because of that fundamental relationship of motion, we have that the final, and this would be some infinitesimally small amount of time later, but the next immediate angular momentum vector must be equal to the previous one, which here is L naught, so the original angular momentum vector, plus that change, that dl, that infinitesimally small change in angular momentum, which of course has a direction. And what's the direction? Well, think about it. The direction of dl, the change in angular momentum, okay, the instantaneous change, is equal to torque. Okay? They are parallel. The torque vector and the dl vector are parallel to each other. Okay? So then we see that the angular momentum must follow the change in angular momentum. Okay, because the idea is that, this is no different than velocity, right? If I have, some instantaneous velocity vector, and then I've got here, I'll do it like this. So I have some instantaneous velocity vector, and I have some change in velocity vector, dv, then the new velocity vector, v final, would look like that, wouldn't it? Because it would follow that change. I mean, that's actually the idea behind circular motion, right? We know that the velocity vector moves because it's following the change, okay? In that case, the direction of delta f, or delta v, excuse me, or dv is parallel to acceleration. So, we've seen that idea before. But here, dl is parallel to torque, okay? And we even saw, if you think about the instantaneous change in momentum, since momentum is always parallel to velocity, it's really the same idea. But in translation, we always saw that force and dp are parallel, okay? Absolutely, okay? So, that's no different. And that idea is fine, right? That is a very easy idea to conceptualize. What is interesting is the way it combines with the cross product. Because the cross product tells us that the torque is always going to be perpendicular to the plane of rotation. So we already have this, I would argue, counterintuitive direction that torque points. And now torque actually has a real effect, because it means that it's then telling the angular momentum where to go, really, okay? So the result is the precession of the rotational axis, okay? Now, obviously, I jump from a definition to saying, okay, well, there you have precession. What do I mean by that? Well, let's look at this picture here, okay? So here we have a top, right? You can clearly see, some sort of wooden spinning top. It's got a pivot point, okay? Contact with the ground. Now let's think about what's happening here. Okay, so a few things to consider. We've got the only force acting in the system is that of gravity. Okay, gravitational force acts at the center of mass of the top, right? Maybe it's not symmetric because the top is more like a cone, right? So somewhere near closer to the top than the bottom is the center of mass, and there's gravity. Wonderful, and that's the only force. Okay, now I guess to be fair, there would also be a normal force, but if we choose our pivot to be right here, which is implied by our coordinate axis, right? We see that, there's the origin. So that's really implied. That's where our choice of pivot is. And there are no non-zero torques other than that created by gravity. Okay. Well, let's do the right-hand rule, all right? Take your index finger for R, pointing in the direction of the displacement from your chosen pivot point to the center of mass, where the only force acts. That creates a non-zero torque with that choice of pivot point, okay? So take your index finger, point it from the origin to that point, okay? Wonderful. Now take your middle finger and point in the direction of gravity. Now they're not perpendicular to each other, so just take the component, right? So take the component of R, we'll call it R perpendicular, and then consider the force, right? So there would be R perpendicular, and then you've got your force of gravity, okay? So now do that. Take your index finger. In other words, your index finger would be pointing exactly to your right. Your middle finger would be pointing down, all right? Because obviously, that there's no problem there. The force is entirely down, and we're just considering the component of the displacement vector that's perpendicular to the force. We're just considering the moment arm. So where must the torque point in that case? Because in that case, you're using the right-hand rule, and R for your index finger and F for your middle finger. Your thumb is the torque. Where does it point? Into the page. Okay, it points away from you, which is into the page, into the screen. All right. So that means that the torque must point into the screen, and we see that here. Okay, we see that the torque is pointing into the page. Okay, it's pointing in what's here called the x-axis, because x here represents into the page. Notice this is not maybe the typical 3D axis that I use with I usually use x, y, and z, but this is still a rotation of the typical axis that I use, so it's still what's called a right-handed coordinate system. So it's fine, okay? But in this case, it would be in the negative x direction. Torque is pointing into the page, okay? And we can see that, it's kind of shown here in perspective to be pointing into the page. All right, so what does that mean, though? What's the consequence of that? Well, torque and angular momentum must be parallel to each other by Newton's second law. So that means that the change in angular momentum must also point into the page. Okay? Right? So that means that the new final angular momentum must follow the change in angular momentum. So after some small amount of time, the angular momentum vector that used to be parallel to the axis of rotation is now over here. Okay, so let's think about that. What does that mean? Well, the angular momentum vector can't move on its own. After all, L equals I omega, right? It's always parallel to angular velocity, which is actually why we knew in the first place that it ran right along the axis of rotation, because by definition, the angular momentum vector does. Okay, it is after all a solid object. It has a defined moment of inertia. So that means that the angular momentum vector has moved because torque has forced it to move. That means the whole object has moved with it. So what we're seeing then is that torque is carrying the object via the change in angular momentum, the dl vector. It is carrying it in a rotational path. Because if we continue to do the right-hand rule, we won't find that the angular momentum vector just goes in a straight line. We'll find that the angular momentum vector, by little segments of dl, will go in a circular path, right? Each of these would be a dl, every one of them parallel to a torque that we could figure out with the right-hand rule in each case. Okay? That is precession. Absolutely, unequivocally, that's precession. It's that the torque creates a change in angular momentum, thus the new angular momentum must follow the change. All right, which causes the motion to precess. Now, could we avoid precession? Yes, if the top was completely upright, so that the gravitational force was not creating a torque. Because in that case, the gravitational force would be anti-parallel to the rotation axis, and well, sine of 180 degrees is the same as sine of 0 degrees. It would be 0, and so there would be no torque, thus no dl. All right, but that would require the top to be perfectly upright, which doesn't actually happen. There's always some deviation from being perfectly upright. So every spinning top precesses. It behaves in a gyroscopic manner. Let's look at then how we can quantify the precession rate, because it turns out that we can actually get this path of precession and find out exactly how fast it's turning. Okay? And that will be a very different number from the angular velocity. They're both going to be measured in radians per second, precession and angular velocity, but you know which one's slower? Precession, obviously, because the top will make many turns, many complete revolutions by the time it makes a complete precession. Okay? All right. So let's look at the derivation here. So we'll start with Newton's second law. All I've done is just rewrite it to solve for dl. All right? So this is just taking Newton's second law, solving for dl by cross multiplying by dt. Then I'm going to acknowledge that dl is L sine phi d theta. Okay? How do I know that? Well, I just we know it from the definition of what angular momentum is, right? Angular momentum is a cross product of displacement and translational velocity. And so the idea here is that, I guess even better, is that here we can think of dl as having, this component, right? It is this component of L, right? And look what d theta is. It's not the same as phi. D theta is the angle of the precession. So it is that component of the precession circle, okay? And then torque is the cross product of, well, the displacement vector from the origin, the pivot point, and the gravitational force. So it's a cross product of R and mg, which then just becomes by the magnitude, because we're only interested in the magnitude of torque, rmg sine phi, okay? And that's just going to be the magnitude of the torque vector, and phi is the angle with the vertical, okay? All right, and this is just the definition of a cross product. All right, and then we're going to say that we'll define the rate of precession, and it makes sense to do so, I'll explain why, as the change in theta over the change in time. And that means that the precession velocity is radians per second. It is an angular velocity. It's just not the angular velocity. It's the angular velocity of precession as compared to the angular velocity of revolution, which we always just call the angular velocity, which is omega. Okay? And notice what letter this is. It's just uppercase omega. Okay? But that's the only time we use uppercase omega for motion is for the rate of precession, distinguished from the rate of revolution. Okay? And that's just d theta over dt, which makes sense because it's just going to be how much of this angle of this circle, which is the precession circle, the path of precession, is covered in a certain amount of time. Okay? So then, if we just say, okay, well then if that's a logical definition for the rate of precession or the velocity of precession, then we can do a substitution here. We can say, okay, well, if it's d theta over dt, then what is it? Okay? All right, this is the component of L that is perpendicular to the xy plane. That's all this is right here. Okay? That's the best way to think about what dl is. Okay? And then this is the angular precession velocity. Okay? And then notice how I've circled here. All I've done is I'm just replacing the change in theta with dl, okay, over L sine phi, right? Well, how did I come up with that? Well, because there's d theta, all right? So it makes sense. If I just solve for d theta, then it's dl over L sine phi, all right? And the dt is still there by definition of an angular velocity, okay? So then we can say, okay, well, we can say, okay, well, that's also going to be equal to torque over L sine phi. Why is that? Well, because we have then that torque is dl over t. See? All I've done is just replace dl over t with torque. And the L sine phi is just along for the ride, okay? And then torque, by definition, is, well, it's rmg sine phi, or just mgr if we put the m out in front. And then since that sine phi cancels with this sine phi, it's gone. So now we just have mgr over L. Okay? And then we can replace L with I omega. What I omega? Well, that's just the moment of inertia of the top and the angular velocity of the top. Okay? So now we have a really nice way of expressing the angular velocity of precession in terms of really just the physical characteristics of the thing that's precessing, whether it's a top or a gyroscope, and how fast it's precessing. That's all you need to know. You just need to know its mass. You need to know what planet you're on. You need to know how big it is. Basically, what is its radius of the thing that's precessing. You need to know what its shape is, because that's going to determine its moment of inertia. And then you need to know how fast it's spinning. Okay? And the faster it spins, the slower the precession rate. You see that? There's an inverse relationship. So really fast spinning things will precess very slowly. Things that aren't spinning so fast will precess more quickly. You see that with tops. Think about when a top is about to really fall over, or it's about to finally stop spinning. It starts precessing more noticeably. It was precessing the whole time, but very subtly. Take a top if you have one, or something that you can behave like a top, and spin it right now, and you will see that as it slows down, it precesses quicker. Which, of course, the equation bears that out, and hopefully the derivation shows where it comes from. All right, all consistent with this figure. Okay, let's do our one example just to make this a little concrete. All right, so a certain gyroscope, okay, and a gyroscope it's a tool. It's also a demonstration. It's a toy. If Google gyroscope and you'll see what they look like. Maybe you've seen one before. I have a sketch of one that I'll show you in a second. That will be included in the example. But here we have a certain gyroscope consists of a uniform disc with a 50 centimeter radius mounted at the center of an axle that is 11 centimeters long of negligible mass. Okay, so we only are going to care about the cylinder part. The axle is horizontal and supported at one end. If the spin rate is 1,000 revolutions per minute, then what is the precession rate? Okay, which I think I cut off by mistake. I should say, then what is the precession rate? Okay. So here it is. Here's the gyroscope. And again, this is typically what they look like. They have some spinning disc. This here can pivot. This is like, mounted on some sort of hinge. And then basically this platform also turns. So there's, so basically, or at least it's free to turn. So this platform is on wheels or is in some way free to turn. And then this is maybe driven by some external power, right? So this disc is spinning often very quickly, and then that will cause this platform to start rotating. Okay, and that is so fascinating, right? Essentially that we can create spin in one axis and then cause rotation in an entirely separate axis. And that is the beauty of precession. I mean, that's why it's used in space stations and satellites. When they want to turn them, they use this property. It actually works. There are gyroscopes built into numerous satellites. There's gyroscopes built into the space station, and they spin, and then they'll then cause rotation in the axis that is exactly perpendicular to the axis that's spinning, right? It's remarkable, right? Okay, so let's just work through the steps, actually solve it. And let's see, anything I want you to pay particular attention to. So here is the radius, that's the distance from the pivot point, okay? And then we have that R perpendicular, which would be the moment arm, is the entire radius because the way it's mounted. If there was some angle, then we just have to take a component. Here we have the disc itself. The disc has a radius of 50 centimeters. We have the torque. Now the torque is just going to come up from the fact that we have, well, first of all, it's equal to dl dt. So the torque, that tells us that dl is also into the page, okay? Into the page. And the reason we know that torque points into the page is, again, from the right-hand rule. We would take R with our index finger. We would use our middle finger to point down, which would represent the gravitational force, and that forces our thumb to point into the page. That's how I know that torque points into the page, and thus dl also points into the page, okay? But where does L point? Well, at this particular moment, at this snapshot in time, L is pointing to your right, the same direction as R, okay? Just at this, this moment. I guess, well, and to be fair, L and R will always be parallel to each other, okay? And it's equal to I omega because that's also the direction of angular velocity. We could use the right-hand rule, right, to, turn our fingers, right? We can represent it here by the little arrows. Turn our fingers in the direction it's turning, and then our thumb must point in the direction of omega, which means it must also point in the direction of angular velocity L, okay? All right. And the disc is spinning at fast rate, 1,000 revolutions per minute. Okay, but that means because of that torque vector that's into the page, that means that the angular velocity vector, the angular momentum vector must follow the torque vector effectively. Truly, it's following the dl vector. Okay, but it must follow that vector into the page, which means that the precession rate is going to be like this. It's a precession path is going to go into the page, right? Eventually, then you'll become parallel to the page again over here, and then come back out of the page and then repeat. Okay, so that's what's going to happen. It's going to precess in a totally different plane. It's going to precess around this axis. Okay, it's going to revolve around this axis here, but it's going to precess around the other axis. In other words, if this is the x-axis that it's revolving around the disk, then the whole gyroscope is going to precess around the y-axis. All right? Okay? All right. So let's just run through it. So here is the precession velocity, angular velocity, mdg r perpendicular over I disk omega. All right. In this case, then we can rewrite the moment of inertia I disk look it up in a table because it is a cylinder. It's just 1/2 mdr squared. That means the mass of the disk actually cancels out. It's just the shape of the disk that matters. Here, this is the radius of the disk. This is the radius of the arm. All right. And then we can just plug in our values. So there's our arm length. Here is our disk radius. We've got gravity matters, and then of course omega matters as well. I converted it from revolutions per second. I converted it from revolutions per minute into revolutions per second. Okay, and then we end up with 0.51 revolutions per second. Okay, that's the precession rate. And I could then further convert this into radians per second. I'll just go ahead and leave it in revolutions per second because it gets the point across that it's much slower. Look at it, right? 1,000 revolutions per minute is, I mean, even when we find out how many that is per second, dividing 1,000 by 60 is still going to be a fairly large number compared to, 0.5, right? In fact, it ends up being 16.7, right? So 16.7 rev per second is the rate of, of revolution. Precession is, some 30 times smaller than that. So it's precessing much slower than it's revolving. And that is the case. That is always the case because of that inverse relationship that shows up in the formula, okay? But besides the numbers, the fascinating part is this behavior. Because what it really looks like, what gyroscopic motion looks like, is it looks like motion from nowhere. It really does. There is nothing in the basic human experience that will tell us that this should happen. It is not intuitive, right? We can train ourselves to get used to it. We can learn it, and we can make sense of it. But it just doesn't come up enough in our everyday lives, and it inevitably looks like motion out of nowhere, which is both beautiful and fascinating, but also can throw you off. So make sure that you have some understanding of it. You can make sense of the vector directions and just think of how it comes from the cross product. Okay? All right. Well, I hope this very short one topic lecture has been both interesting and informative. Thank you so much for watching.